Google File System GFS. Introduction to a file system. A file system determines how the data is stored and retrieved. Distributed file systems manage the storage across the network of machines. Added complexity is due to the network. GFS, SDFS are distributed file systems. Before we start the topic of this particular lecture, let me introduce you to the motivation and the background for Google File System. So, Google is storing its data over a large number of computers which are having the storage within it. So, it is exploiting the storage of large number of computer, which is also called as a commodity hardware. This particular large number of computers which are connected through the network are now used to store the information which the Google requires for its application. Now, once having stored this information on a large number of computers, maybe thousands or more, then a large number of clients required to access these particular data which is stored in the distributed environment simultaneously without any problem. For this, Google has devised a file system which is called as a Google File System, and after that SDFS file system Hadoop has also made the same kind of file system with different terminologies within it. So, let us understand this Google File System. So, in the Google File System description, that is why we are going to make, why, because the distributed file system existed earlier also, but as far as modern day applications are concerned, which involves the large data sets or large amount of information which is to be stored, which cannot be stored at one place, which is stored in a distributed systems. If it is stored, then how many clients can simultaneously access it? So, for that we are going to see a thing which is called a Google File System or a file systems, which will facilitate not only to store the file over a large, with the help of a large number of computers, and also it will support how the large number of clients can access to that stored information in a distributed system. So, the introduction says like this: Google processes its data in a computing cluster. Google makes their own servers use commodity class CPUs running customized versions of Linux machines, meaning to say that the cluster comprises of several servers is called a cluster. Maybe they are networked with each other. Now, each of these servers, they are running the Linux operating system within it. So, Google will make use of this particular scenario to implement the Google File System. Now, this will seek to maximize performance, and how this is specifically measured is not public information. Then novel switching, power supply, all these are generic problems of infrastructure that is going to solve if the commodity hardwares are used instead of big machines like supercomputers. That is the philosophy of a Google. So, GFS utilizing these commodity hardwares and which does not require a very big infrastructure to support it. So, let us go for the introduction of a GFS. GFS is scalable distributed file system for a large data intensive applications. Shares many of the same goals as previous file systems such as performance, scalability, reliability and availability. They were there in earlier file system also, here also they are also will be there, but in addition to that it is going to basically support the large data intensive applications. So, the design of GFS is driven by 4 key observations, that is, if the commodity hardwares are there, then there is a possibility that the failures will be a norm, it is not an exception. Now, another important thing is the file size is a big huge. So, it is a huge files which are basically are going to be supported in the modern applications. Third one is the mutation of a files and the benefits of co-designing the applications and the APIs to access all that things are basically these are the main point to be supported in a Google file system. Google file system assumptions, the hardware failures are common, that it has become a norm. Why? Because it is a commodity machine, they are inexpensive commodity machines, they are prone to failures and they may fail also. Similarly, as far as the files are concerned, now here modest number of huge files are there, and see these files of a bigger size are now very common in this kind of environment. So, hence they are to be supported optimally, whereas small files are not that very common. So, basically it will not focus on optimizing about the small files. The workloads are two kinds, mostly they are of reads and writes. So, writes means the files are written, that is a big data set is generated once in the form of writes, and after that most of the time it will be read only operations. So, two kind of operations are supported. So, large streaming reads of 1 megabyte or more and small random reads. So, small random reads will not be more focused. So, only the large streaming reads or a sequential read operations will be supported here. So, sequential append to a file by 100 of data producers will become an important issue as far as handling workloads are concerned. High sustained throughput is more important than the latency. So, the response time for individual read and write operation is not very critical here in this kind of scenario. Google file system design overview. So, in Google file system, these are the following components which will be participating and realizing this file system operation. The first one is called a master, there will be a single master and which will handle the centralized management. The second entity here is called file, which are stored as the chunks. So, chunks are the another important entity in Google file system. Chunk is nothing but a fixed size of 64 MB is called a chunk, and the file is nothing but file is stored in a form of a chunks. So, if a file is bigger than 64 MB, then file may contain more than one chunks and the entire data of a file will be stored. Reliability through replication. These chunks are stored on the commodity hardware which are prone to the failures. So, the only way to overcome from these failure fault tolerant is basically go for the replication. So, by default the replication number is 3, that means a particular chunk is replicated in 3 different chunk servers. Now, the next entity is called data caching. Due to the large size of data sets, data is not cached or is not required to be cached at the client as well as at the chunk servers. However, the chunk servers are running the Linux file system locally. So, Linux local caching is good enough to be supported here. No external or no extra management of caching is supported here in Google file system. As far as interface is concerned, it is suitable to the Google applications or Google apps. It will create, delete, open, close, read, write, snapshot, record, appends. These are the different interfaces which will support these operations that we will see in this part of the discussion. Now, Google file system architecture. Let us go through this architecture. There will be a single master which is shown over here. There will be single master and there will be several clients as far as, and the data will be stored on several servers which are called as chunk servers. Now, the data is not flowing across client and master that you can see, rather the data is flowing from client to directly to the chunk servers which stores these particular data. So, data flow does not flow across the GFS master. Now, let us go and see what the master does in Google file system. So, the role of the master basically it's nothing but a metadata server. That means it maintains all file system metadata, that means information about the data where it is stored or information about the file system. It's called metadata and that is being maintained at the master. So, basically master will deal with handling of the file namespace, handling file to chunk mapping, and it will also handle chunk location information, keep all the metadata in the master's fast memory. Let me explain you through this particular example. So, the file namespace, that means once the client gives a file name and the directory will form the file namespace. File namespace is maintained by the Google file system master. So, and second information which is maintained by the master is about the chunk servers. So, two important information which is maintained by the master. The first one is basically called namespace and the second one is about the chunk servers. These informations, the metadata is stored at the master. So, file to chunk mapping will be handled using these two information by the master. Chunk location information will be given. So, the file is stored in the chunks. So, those information will be provided through the chunk servers by the master. That information also, chunk placement information is also with the master. Now, it will keep all the metadata in the master's fast space. Now, location of the chunks and their replicas. Master does not keep the persistent record and operation logs for persistent and memory is maintained. Pull it from the chunk servers. Master as the monitor no cost, meaning to say that the master does not maintain the information about the chunks or the location of the chunks. Location of the chunks are maintained by the chunk servers. However, the master continuously pulls from the chunk servers and fetch this information whenever is required. So, it is not going to store at the master level. So, master does not keep this persistent information of the chunks and the replicas. So, operations for the persistent and the recovery, for that a log is maintained. So, all the informations or the metadata which is stored in the master, a log will basically be maintained for its persistence. So that means whenever there is a failure at any end, at the end, so master will use this log information, or log will be used to restore or recover it. So master as a metadata server, it will monitor. So it will monitor, as I told you, that master does not keep the information about the chunks. So the master and the chunk servers master use this particular heartbeat messages to detect the state of these chunk servers and communicate with these chunk servers periodically. Now whenever master requires the information of the chunks which are managed by the, or which are stored by the chunk servers, using these heartbeats and piggyback this information to fetch the details of the chunks. And so that is why this will communicate, master will communicate with the chunk servers periodically, and also not only to get the health of the chunk servers, but also fetch the information of chunks from it. Now master is basically having a centralized controller. It will also monitor the system wide activities. It will manage the chunk replicas in the whole system. So there is a single master which will simplify the design of the system. It will control the chunk placement using the global knowledge, because the master is having the complete knowledge of the chunk servers, and the placement of the chunk can be decided globally. So the bottlenecks are to be resolved in the sense the client do no read write data through the master. That means client need not have to do the read and write for the data operations through the master. So master is free. So the clients can directly access the data from the chunk servers. Now the clients cache the metadata only. So clients typically ask for the multiple chunks in the same request, and the master can also include the information for the chunks immediately following those requests. So these particular provisions will free the master to be referred for read and write through operations from by the client. So client is not required to access the master for each and every single operation. For data related operations can directly be handled between client and the chunk servers. Master is not basically involved in it. Now caching metadata that is cached on the client after being retrieved from the master, only kept for a specific period of time to prevent the stale data. So the caching for metadata is only done, not the exact data. So file caching, clients never cache the file data, as I explained you earlier. So chunk servers never cache the file data, because Linux buffer does that caching for the local file. So that will be sufficient in Google file system. So file working sets are too large, and that is why it's not required also to be cached. Why? Because a big size files which are streamed as far as the operations are concerned are not required to be cached. So obviously when caching is not there, then it will simplify all the problems or issues of having a cache with the problems like cache coherence. Now GFS chunk. So chunks is the most important part of as far as the design is concerned. So the chunk size is 64 MB. So chunk is stored as the plain Linux file on a chunk server. So advantage of keeping large chunk size is that it will reduce the client and master interaction, as I told you earlier in the previous slide. So one request per chunk suits the target workload. Client can cache all the chunk location for multi-terabyte working set. So only the metadata is cached for the chunks. So obviously if this particular chunk size will reduce the size of the metadata also, which has to be kept in on the master. So, disadvantage of keeping a large size chunk is that chunk servers can become the hotspot for some popular files. So, this particular problem can be handled in future also with some point of research that the clients who are already accessed those particular data can become the servers for the other clients, and hence the hotspots can be removed, but this is for the future scope. Of improvement. So, this particular hotspot problem is very practical and it requires some innovative solutions to be overcome. So, chunk locations. Master does not keep persistent record of the chunk replica locations. As I mentioned in the previous slide, master polls chunk servers about their chunks at the startup. Master keeps up to date through periodic heartbeat messages. Master chunk servers easily kept in sync when the chunk servers leave, join, fail, restart. So, once if the master is not keeping the information about the chunk replica locations, then it will allow the master and the chunk server to be kept in sync at all the point of time easily. By not keeping the chunk replica locations at the master, now the master and the chunk server can easily be in the sync with the help of the heartbeat messages. So, now when the chunks are out of the master, then basically these chunk servers can leave, join, fail, restart at a very regular interval and can be handled separately out of the master. So, chunk servers has the final words over what chunk it has. Operation log. Persistent record of critical metadata changes are stored in the log critical to the recovery of the data. Changes to the metadata are only made visible to the clients after they have written to the operation logs. Operation log replicates on a multiple remote machines. So, before responding to the client, operation log must have been flashed locally and remotely. So, master recovers its file system from the checkpoint and the operation. So, all these aspects, how the checkpointing and the recovery we have already covered. So, that concept is used so that the master becomes the fault tolerant. So, if the master is becoming inactive or a faulty, then it will be recovered with the help of a checkpointing which is maintained in the stable storage or with the help of a mirroring of the master node. Now, consistency model. Atomicity and correctness of a file namespace are ensured by the namespace locking. Now, after successful data mutation, writes or read appends, changes are applied to the chunk in the same order on all the replicas. In case of a chunk server failure at the time of mutation, it is the garbage collected at the soonest opportunity. So, regular handshakes between master and chunk servers helps in identifying the failed chunk servers and detect the data corruption by checksumming. So, this simplifies a more complicated consistency model. This will good enough to solve the consistency issues. System interactions, leases and mutation order. So, master grants the chunk lease to one of the replicas, and this particular replica is called a primary replica. So, all the replicas follows a serial order picked by the primary. So, leases times out at 60 seconds and leases are revocable. Let us see the interactions. So, the first step is the client asks the master which chunk server holds the current lease of the chunk and the locations of the other replicas. This is the first level interaction. This interaction happens when a client wants to access a particular file with a file name and a data at a particular location or a index. knowing the size of the chunk, it can, this particular index is nothing but an offset in a file, which particular inside a file that data which is required by the application. Having calculated the index and the file name, this particular message will be sent to the master. So, master asks the client asks the master about which chunk servers holds that current lease of the chunk and the location of other replicas. Master will respond by giving the identity of the primary and the location of the secondary replicas. So, this information will be used by the client, and the data will be pushed. This is the data, red line shows the data will be pushed directly in a linear fashion to the primary and secondary replica servers. So, this particular flow of the data will use the simple network bandwidth. It will not follow any topology. So, it will follow a linear fashion. The data will be pushed here to all the replicas, because now the client knows the primary as well as secondary replicas, and it will form a chain and the data will be pushed. Fourth step says that once all the replicas have acknowledged the receipt of the data, the client sends the write request to the primary. Now, here it says to write. So, data which is pushed to all the replica server, that is primary and secondary replica. Now, the client will issue a write command to the primary replica. So, the primary is now having the lease of all the for maintaining all the replicas. So, the primary assigns a consecutive serial number to all the mutations it receives, and it will provide the serialization, and it applies the mutations in that serial order. So, the data in the form of the chunks will get assigned the serial order or serial number from the primary replica, and these serial numbers are given or assigned, and these secondary replicas will use that serial number to order all the mutations. Now, the primary forwards the write request to all the secondary replica. They apply the mutations in the same serial order which I have told you. The step number 6 says that all the secondary replicas, they will reply to the primary replica that they have completed the operation. Now, having completed all the operation, the primary replies to the client with the success, or if it is not success, then some error message it will provide to the client. So, that was the system interactions. So, system interactions has two parts. One is called data flow, that means data will be pushed through the network in a linear fashion among all the three servers, that is primary and two secondaries. So, the data is pipelined, that is called pipelining, and data is pipelined over TCP connections. A chain of chunk servers form a pipeline. So, each machine forwards the data to the closest machine, that is called data flow. Now, second level interaction is the atomic record appends. GFS provides an atomic append operation called record append, and a snapshot means that it can make a copy of a file or a directory tree almost instantaneously. Let us see the read algorithm. So, the application originates the read request here to the GFS client, indicating the file name and the byte range. So, out of this particular byte range and knowing the chunk size, this client will compute the chunk index and copying the file name as it is. So, inside file, the client will compute the chunk index, and this particular pair, the file name and a chunk index, will be given to the master, and the master in turn will provide a metadata for the chunk that is called a chunk handle, and also the replicas where that chunk is stored. This information will be passed on from master to the client. Now, the client then directly send the messages, that is the chunk handle and the byte range, directly to the chunk servers, and these chunk servers will fetch the data from the file and will be given to the client, and then the data will be passed on to that application. That becomes the read algorithm. Let me read out all the steps. So, the application originates the read request, GFS client translates the request from file name byte range to the file name and chunk index and send it to the master that I have explained. The master responds with the chunk handle and the replica locations. Now, the client picks the location and sends the chunk handle and a byte range with a request to read to that particular location. Chunk server send the requested data to the client, and the client forwards the data back to the application. So, that becomes the read algorithm. About write algorithm, I have earlier explained during the system interactions, but let us go ahead again. So, the application originates the write request, GFS client translate the request from file data to the file name and data to the chunk index and send it to the master. That we have already seen in the read algorithm. Now, master responds with a chunk handle and the replica location, that also we have seen in the read algorithm. Now, the client pushes the write data to all the locations that I have already explained in the previous slide of the system interactions. The data is stored in the chunk servers in its internal buffers. When the client sends the write command to the primary memory, then the data will be muted, then the data will be written. So, the primary determines the serial order for the data instances stored in its buffer and writes the instances in that order to the chunk. Primary sends the serial order to the secondaries and tell them to perform the write operations. Secondaries performs the write operations to the primary's request. So, primary responds back to the client. Now, if these write fails at one of these chunk servers, then the client is informed and this entire operation will be retried again to complete the write operations. So, let us see this particular interaction. So, the data will be pushed, data will be pipelined to the primary and both the secondary servers. The primary then issue the sequence numbers like this, and these sequence numbers will be now maintained as far as the sequence number order is maintained for storing that particular data for the write operations. These particular serial order is maintained in the chunk and they are being communicated to the from primary to the secondary storage. So, having written that sequence order messages into the chunks, the secondaries respond to the primary about the completion of the operation, and Thereupon the primary responds to the client about the success. Now record append operation. As I told you that the file is created once and then it is not updated randomly, but the append operation is supported. So the application, so let us see about the append operation which is supported here. So we have seen the read, we have seen the write, now we are seeing the append operation algorithm. Application originates the record append request, GFS client translates request and send it to the master, master responds with a handle, client pushes the write. So primary checks if the record fits in the specified chunk. If the record doesn't fit in the specified chunk, then primary will pad the chunk, tells the secondary to do the same and inform the client. Client then retries the append with the next chunk. And if the record fits, then the primary appends the record, tells the secondaries to do, receives the response from the secondaries and send the final response to the client, that is data to all the locations. So it is almost same as the write operation, but it will be written at the end, that is called the append operation. Master operation, namespace management and locking. Locks are used over the namespace to ensure proper serialization. Read and write locks are used. GFS simply uses the directory like file names. GFS logically represents this namespace as a lookup table mapping full path name to the metadata. So if a master operation involves a file name, a path name, read locks are acquired on all these path names, and either the read or a write lock on a full path name is being applied. So let me mention that the file name and its index is stored not in a form of a directory, but in a form of a lookup table which is being hashed. So using this particular change, the namespace lookup is very efficient here in Google file system. So chunk replica placement, creation of initially empty chunks, use the underutilized chunk servers which are spread across the racks, and re-replication, that is started once available the replicas fall below the setting. So re-replication is performed so that all the empty servers are properly utilized. Rebalancing, the master rebalances the replica periodically, examines the distribution and moves the replica for a better space and load balancing approach. Garbage collection, deletion logged by the master. So the file renamed to the hidden file, deletion timestamp kept. So all these particular provisions are there for garbage collection. Why? Because if a particular chunk is failed, then basically another chunk is already in place. So those failed chunk will become a garbage. So these garbage will be periodically scanned and checked. Periodic scan of master's chunk namespace is also done. So stale replica detection using this scanning is already done. Fault tolerance, so this is also very important aspect in Google file system. So fault tolerance is achieved with a fast recovery, chunk replication and master mechanisms. Fast recovery, master and chunk servers are designed to restore in a few seconds. Chunk replication across multiple machines, across multiple racks are being made. So master mechanisms keeps log of all changes made to the metadata. Periodic checkpoints of the logs are maintained. Log and checkpoints are replicated on a multiple machines. So whenever a master state is replicated on a multiple machines, shadow master for reading data if the master is particular down. Now for further reading on this particular topic, you can refer to the paper by Sanjay Ghemwat, the Google file system, which is available at the Google link. Conclusion: GFS is a distributed file system that supports large scale data processing workloads on commodity hardware. GFS has different points in the design space. Component failure are a norm and optimize for a huge files or a large data sets operation or a computation. GFS provides fault tolerance by replicating the data, fast and automatic recovery, and doing the chunk replication. So, GFS has made a very simple centralized master that does not become a bottleneck in this particular problem. Thank you.